Okay, good morning. This is September 19th, 2017. This is the fourth class of Fundamentals of the Vitreous or Glass State. We have seen the general properties of glass, especially the viscosity, two full classes on the viscosity of glasses, and then relaxation, TEG, and the definition of glass. Today, we are going to talk about the structure of oxide glasses. You already know that there are many types of glasses. Organic polymer, that is high molecular weight organic glasses, metallic glasses, chalcogenide glasses, all types of non-oxide glasses. But the vast majority of glasses, especially commercial glasses, are made of oxides. So we are going to talk about the structure of oxide glasses. And structure, of course, is one of the features that distinguish glasses from crystalline materials. And also, the structure determines the properties of glasses. Especially because they do not have crystalline grains. Like in ceramic materials, the properties are dominated not only by the chemical composition, but also by the grain size or the grain size distribution, the number of crystalline phases, the properties of the grain boundaries, the texture or not texture of the grains, etc., etc. In glasses, the properties are dominated by the structure, which is in turn dominated by the chemical composition. That's a very nice feature of glasses because in principle, if we knew the laws that determine the properties, we could relate all the properties to the chemical composition. This is a very, very rich and intense research topic at the moment. Relationships between glass composition and properties. Optical, electrical, mechanical, thermal, rheological, etc. So let's then take a look on oxide glass structures. If you look at Google for glass structures, please, I'm not talking about, glass structures such as this nice one here. There are many, many very nice, interesting macroscopic glass structures. Today we'll be talking about the microscopic, the atomic structure of glass, not the macroscopic structures that can be made of glass. And again, every class I review this special plot of some property versus temperature because there are many, many aspects related to glass, the fundamentals of glass science, which can be seen schematically in this plot. And one of them is that one has a liquid, then we manage to supercool a liquid, averting crystallization, so we come in this way here. At some stage, the relaxation times, the structural relaxation times become so large that the supercooled liquid can no longer relax, and supercooled liquid freezes. Just to remind you, the meaning of freezing is a temporary state. The material becomes rigid temporarily. That's the word, the meaning of freezing. It's different from solidifying. solidifying means crystallizing, becoming a real true solid. But a glass is not a real true solid. It has many properties of solids because it's frozen. It's a frozen supercooled liquid. We'll talk more about this. But so one key question is the structure of this liquid different from the structure of the glass? Or is it the same? We know that the structure of the glass and the structure of the supercooled liquid are different from the structure of the isochemical crystal phase. The crystal phase is the same chemical composition. But how close is the structure of the supercooled liquid to the structure of the glass? This is one question we are going to respond today. Excuse me. Anyway, we have already seen in the last class that glasses also depend on the thermal path. For a glass of a given chemical composition, which is cooled very, very fast, such as a fiber, or a spot cooled, or a spin cooled material, we will have a structure which is somewhat different from the structure. This is room temperature here, from the same material that has been cooled at a different rate. And to prove that, I'm going to show some slides in a minute, but just before and just to recap the last class, remember that this is the fictive temperature. The fictive temperature is one temperature where the structure of the supercooled liquid was frozen. And it came very significantly with the cooling rate. But the question we are going to try to answer today is whether the structure of this material here is different from the structure of this material here, and how different they are from the structure of the supercooled liquid. These are very nice NMR studies by Professor Jonathan Stebbins, published a few years ago, where they had, just to give you an example, a series of, this is soda, alumina, boric oxide, silicon oxide glasses. And these are calcium, alumina, boric oxide, silicon oxide glasses. Borate glasses, so they have a lot of boron, and boron is very good for NMR. So if you do an NMR experiment, you can distinguish boron at coordination 3, boron, oxygen, oxygen, boron at coordination 4. And you see the annealed material, annealed means low fictive temperature, or slow cooling rate. If you look here, they have different ratios of boron 4 to boron 3, different ratios of boron 4 to boron 3. This is a very finest detail of the structure of a new material versus a fast quenched material with high TF. It's the same material. So in both cases, you can see that the area of under these peaks will give diffraction of boron 3 to boron 4, and they are somewhat different. Not completely different, because it's the same glass, but these kind of plots, and there are many others in the literature, show that the cooling rate affects the finest details of the glass structure. So it's not only a schematic plot that we do. I mean, the actual structure is different depending on the cooling rate or on the thermal history of the material. Now, what about the effect of temperature? I have asked you, is the structure of the supercooled liquid different from the structure of the glass or not? If you look at these plots, I'm going to explain in a minute the meaning of Q3, Q4, etc. But the Q3 is just the average number of, in this case, is silicate glasses, so the average number of corners that are shared. So each SiO4 tetrahedron has 4 corners. For the disilicate crystals, you expect 3 corners to be shared in the structure. If you look at the crystalline phases, for instance, this is potassium disilicate, sodium disilicate, barium disilicate, lithium disilicate. Their crystalline phases all have 100% Q3. If you look at the structure, and the structures of these disilicates are known by X-ray diffraction methods, all tetrahedra share 3 corners. 3 corners are shared in a 3-dimensional network. But if we look at the glasses, let's take the potassium silicate glasses, the fraction of Q3 increases with temperature, so the structure changes with temperature. This is one way to look at the glass structure. There are several ways. I'm going to show you in a minute. But at TG, it freezes, as we expect. So, for this particular glass, we have about 82% at TG here, 82% or so of the tetrahedra are sharing 3 corners. For the lithium disilicate, 50% of the tetrahedra are sharing 3 corners. So this is a measure of how different the structure of these glasses can be, but most importantly, the structure of the glass here is about the same, the glass here below TG is about the same as the structure of the supercooled liquid. It has maybe 1% less or more Q3, but this is just the effect of temperature. The fact is that the structure of the glass is the same as the structure of the supercooled liquid, just a few degrees above TG. And this is true for all materials. Look at the sodium disilicate. The structure of the glass is about the same as the structure of the supercooled liquid. So that's another indication that glasses are just frozen supercooled liquids. They have the same structure, basically. It's not like a solidification process. If we have like a crystallization, in a crystallization, if you're looking at the structure of the material during crystallization, would move from here to here. The structure of the crystal phase is 100%. If we are looking at the structure of this material here, we would move from the supercooled liquid with 50% Q3 to the crystalline phase with 100% Q3. This is the kind of structural changes that happens when we crystallize, when we solidify permanently the material. So this is not a permanent solidification, it's just a freezing in of the structure, a temporary phenomenon. And then if we wait for some time, as we had seen in the previous class, the glass will relax. And if we wait longer, then it will eventually crystallize. So glasses their frozen structures will relax with time. It's spontaneous. You just have to wait. If we are very close to TG, it will take minutes. If we are well below TG, it will take ages, geological ages. But they are always relaxing. These glasses here are relaxing. All glasses are relaxing towards the super cool liquid. This will be the super cool liquid extension. So the relaxation process would be moving from here to here. But it doesn't stop here. It continues to go towards the crystalline phase, if we wait long enough. Any questions about this? Benjamin, you're a glass structure expert.
It's good.
It's good. You agree with this?
I'm just wondering why the B2SI and the lithium don't taper off like the sodium and potassium.
This is a very good question. I was hoping that somebody would ask this. Why there's no freezing in here and here at EG? Because of this. These are calculated from a thermodynamic model. This is only the calculated number of Q3 in this gas. So if you calculate, you don't see any TGs, pure thermodynamics. So we are seeing here is the super cool liquid. Super cool liquid. These are experimental, see? Experimental. Then it freezes in. If you calculate it, in calculations there is no TG. So this is a very key question, and you perceive this. Thermodynamic calculations do not get it, because it's equilibrium. Okay? I like very much this plot because it conveys the idea that the structure of the glass is just the same as the structure of its supercool liquid, a few degrees above PG. Of course, if we heat the glass a lot, the supercool liquid a lot, we start to depolymerize more and more this structure, more and more this structure. This is the equivalent of the degree of polymerization in the polymer. The more, if you have a Q4, like pure silica glass is Q4. All the tetrahedra are sharing the four corners, highly polymerized. When we add sodium or lithium or calcium or anything, we break bonds and start to depolymerize the structure, and also the temperature has a similar effect. And that's why the viscosity, we have seen that the viscosity curves are not Arrhenian. They are not Arrhenian because the structure changes with temperature of these fragile glasses. So it's not Arrhenian. For a Q4 glass, such as silica glass, that the silica glass will be all Q4 and will not change with temperature. So the viscosity curve is Arrhenian, right? So we're starting to correlate properties and correlate structure with properties. This is a schematic plot of a solid and a supercool liquid. So if we could see the atoms in a crystalline solid, they'll be vibrating. They'll be vibrating around some average position. In the liquid, in addition to vibrations, they will be, wandering around and moving from one position to the other. This is a nice cartoon of atomic movements in solids and liquids. Another one that I have already shown to you, is a schematic plot of these specific heats. the crystal, this is the specific heat versus temperature. The crystalline phase has a typical schematic specific heat, such as this one, and then in the end of the class, I like to see the specific heats that you found for your particular glasses, but I hope you found something similar to this. And in most cases, the specific heat of the glass is higher, but in several cases, just above that of the crystal phase. Not as different as this schematic plot that I'm showing you, but very similar. But they're always larger. The specific heat of the glass has to be larger than the specific heat of the isochemical crystal phase. And then, of course, we have the specific heat of the super cool liquid, which will not exist here. We have to extrapolate here using some polynomial function because it becomes a glass. So it does not exist here unless you cool the material slower and slower and slower and slower, then you have a specific heat of the super cool liquid. But in general, this is the kind of plot, and in many cases there's even some overshoot here. You come here, there's an overshoot, and then comes some liquid. So in the end of the class, we'll take a look at real values that you have captured in the internet about specific heats. So to summarize a little bit of this story and coming back again to the definition of glass that we started to discuss last class, you know, we have to realize that glasses, they have many solid-like properties, you know. They are hard, they're brittle, they break. The fracture is catastrophic if you drop them. The elastic modulus or the shear modulus are non-zero. They resist stress like a solid. You know, they have elastic deformation like a solid. They even ring and resonate. Glasses ring. Well, this is full, so it's not ringing so much. And resonate like a solid. This is like a solid, right? On the other hand, they also have liquid-like properties. As I have shown before, the structure is exactly the same as that of the parent supercool liquid. They spontaneously relax to the supercool liquid. This is last class, we have seen this. And they flow, they relax and also flow with time. And finally, they crystallize. If you wait long enough, at any temperature, they will tend to crystallize. And this is real solidification. So, glass is a kind of a friend of mine used to say, and this friend of mine is called Professor Arun Varshnaya, very famous professor of glass science and technology. He says that glasses are transgenders. They're not so sure if they're solid or liquid. They have the properties of both. And that's why in the proposed new definition that we're discussing with you, we say that glass is a non-equilibrium, we agree with that. Non-crystalline, we agree with that. Condensed state of matter, we don't say solid here. Many definitions describe glasses as solid. We don't think glasses are true solids. They have several properties of solids, but they also share properties of liquids. So we prefer to say that it's a condensed state of matter that shows a glass transition. You now know what the glass transition is. The structure of glasses is similar to the structure of their parent supercooled liquids, they spontaneously relax toward the supercooled liquid state. And the ultimate fate is to solidify or to crystallize. That's why we like to use all these words in the definition. Non-equilibrium, non-crystalline, show a glass transition or relaxation, and solidify or crystallize. So 4 words in our proposed new definition of glass. Although not many people agree with this definition, but we'll do our best to discuss and explore this improved definition of glasses. Silica glass, RDF exercise. So, radial distribution functions. This is an interesting concept. Let me ask you a question, and I'm going to give you 2 or 3 minutes to think. If you try to visualize in your heads or in your notebooks a very simple cubic crystal. First crystals, and then we move to glass. Very simple cubic crystal. So you can draw in your notebooks a cubic crystal. And then there's no need to draw all the other cubes, but if I ask you to get one atom as a reference and then draw a curve like this, simply the number of atoms at a distance r from that central atom which is taken as a reference. Let's say that this is the lattice parameter A. Let me give you 2 minutes. I want you to draw a schematic curve. How many atoms are cut by a sphere of radius r? So if I have a sphere here of radius r, it will be 0, 0, 0, 0, 0, 0, 0, and then a certain number of atoms. 0, 0, 0, 0, a certain number of atoms. Let's try to do this exercise so I don't speak so much and you think a little bit. How will be the radial distribution function of a simple cubic crystal for the 3 first neighbors, 3 nearest neighbors from that atom taken as the origin? I'm sorry?
Are you asking for us to do this calculation by a simple cubic extrusion?
Yes, simple cubic. CS. You have done this years ago in your material science classes, but let's remember a little bit. And then I'm going to explain the concept of radial distribution function. Okay, let's then solve this simple exercise. If we have then a very simple cubic structure, the number of atoms which will be included in a sphere of radius r will be 0, 0, 0, 0 until we meet the first neighbors will be 1, 2, 3, and then 1 here to this side, 1 down, and 1 that way. So it'll be 6, right? So at the distance will be A. So at the distance A, we have 6. Then the second nearest neighbors will be these guys here. See? 1 here, along this direction. So in this plane here, we have 1. Then in the other plane, another 1, another 1, another 1. In the other plane, 4. In the other plane, 4. So how many we have? 12. What's the distance? What's this distance here?
A square root.
A square root of 2, right? So A square root of 2, somewhere here, we have 12. Oh, I cannot plot 12, I'll put here. 12. 12. And then the third nearest neighbors will be this one guy here. How many we have in the upper plane? We have 4 in the upper plane, 4 in the plane below. So you have 8 guys at which distance? So it'll be somewhere here. We have 8 atoms. So these are delta functions for a perfect crystal. For a perfect crystals, these are delta functions. 0, 0, 0, 0, 0, 0, 0, and then 6. 0, 0, 0, 0, 0, and then 12. Oops. 12, and then 0, 0, 0, 0. Eight. 0, 0, 0, 0, and then 8. Now, the nice thing about this is that when we do an X-ray diffraction, if we had a lot of these cubic crystals in a powder with zillions of these cubic crystals, and we do an X-ray diffraction experiment, so the intensity versus the diffraction angle, you normally get, a diffraction spectrum. This, of course, would continue if we go. And this is the X-ray diffraction spectrum of a powder containing any of these crystals. The nice thing is that if you do a mathematical operation, a Fourier transform of this spectrum in the real, this is the real space, this is the real space of the crystal, and this is the Fourier space. A Fourier transform will give you this, and vice versa. A Fourier transform of this will give information about the real space. Just a mathematical operation. And that's what people use to grasp information about the structure. Just a Fourier transform. This is fine for crystals. What happens then if we take an X-ray diffraction or neutral diffraction pattern of a glass, this is the result. A Fourier, this is an X-ray diffraction of a glassy material, in this case pure silica glass. It has been filtered and calculated, but it's a clean version of an X-ray diffraction, of a silica glass. In this case, they have changed the temperature. Because this is a simulation. This is just a simulation, 2000, 2007, almost 3000 Kelvin, 4000 Kelvin. But the nice features is that even the X-ray diffraction of a glassy material has at least two peaks, in this case of silica glass. It's a very nice peak here, a very nice peak here, and then it has a very wide peak here. In these two peaks, it's not like a crystal which had many peaks because of the order structure, but this shows that the structure of glasses is ordered at very short distances. For instance, the silica glass, we have the silicon-oxygen distances. The silicon-oxygen distance come from here, 1.5 angstrom. This is in angstrom. This is already, this is already the Fourier transform of the X-ray diffraction. The Fourier transform of the X-ray diffraction gives information in the real space. And it's angstroms here is already the real space of the glass. So 1.5 angstrom, more or less, is the silicon-oxygen distance, which is exactly the same as the silicon-oxygen distance in crystalline, for instance, the crystalline form of silica glass. And this peak refers to the oxygen distances. 2.5 angstroms or so is the oxygen distance in this SiO4 tetrahedra in the crystal. In the areas under these curves gives the coordination number, which are exactly the same as in the crystal phase. So glasses, in this, I'm giving only one example, but there are many examples in the literature. There's a whole community that works on glass structure. So the structure of glasses, silicate glasses in this case, at short range order is exactly the same as the structure of their isochemical crystals. They start to lose ordering in this third peak. And this third peak can be analyzed, and it shows the silicon distances, which is how these tetrahedra are interconnected. And that's where the structure loses its regularity. So if we look now at the silicon-oxygen-silicon distance, and the analysis comes from this third, very wide peak here, we can see and then calculate back from the distance, we can calculate back the angles of this, the variation of angles. And this is the variation of angles. P of theta, the probability of a certain angle theta, from 0 to 1, and theta is this angle. It varies significantly from 120 to about 180 degrees. Whereas the crystal also is not perfect. This is a real crystal, A real crystal is not completely perfect, crystallite in this case. The angles vary from 130 to 160. This difference here is enough to give very sharp peaks in an Xrd experiment for the crystal and very shallow peaks for the glass. So if we did here the Xrd spectrum for glass, the intensity 2 theta, that's what we get. This is Xrd spectrum of a glass, and this for crystal. And these peaks here are related after we Fourier transform related to this one, and this one in real space. This is real space already, so it has been Fourier transformed. And this is the diffraction angle 2 theta. Silica glass. And this is how people do a lot of X-ray diffraction or Newton diffraction experiments to get information of this type here. What's the distance between the first neighbors? What's the coordination number? What is the distance between the second neighbors and the coordination number? And then the distribution of distances or angles of the paired neighbors, and so on. This is one method. There are many other methods to gather information about glass structure. But this is a powerful method that only gives, this type of information. Another interesting type of information, which then needs the molecular dynamic simulations and some sorts of computer simulations to be able to fit the diffraction spectrum to that distribution of angles. You see a distribution of rings. These tetrahedra, they form rings. Let me see if I have a picture of a ring here. Schematic picture here of rings. Each guy here represents a tetrahedron. So you can have one tetrahedron, 2, 3, 4. So this is a 4-member ring. This is 1, 2, 3, a 3-member ring. A 5-member ring. The crystal phase, this is the crystal phase, have 6-member rings. All the tetrahedra are connected with 5 other tetrahedra, and they form rings. This is the structure of crystalline. But the structure of glass has a distribution of rings, and these are results from different authors, including our colleague here, Professor Pedro Rino here, UFSCar, and one of my friends, Professor Liping Huang, in Rensselaer Polytechnic Institute in New York. But they are experts in molecular dynamics, so they use information to draw these curves of a distribution of ring sizes. So in silica glass, there is a certain fraction of 3-member rings, 4-member rings, 5, 6, 7, 8, 9, up to 10-member rings. The average is more or less at 6. 6 is the number for the crystal phase. So the average for the glass is also 6, or close to 6. But there is a distribution. So this is the kind of information that you need to distinguish the structure of a glass from the structure of its isochemical crystal phase. A distribution of rings. The key win that I have shown before, the short versus medium range distances, distribution of angular distances, and so on. people gather all sorts of information to assemble a picture of the structure of a glass. It's quite complicated, actually, much more complex than assembling the structure of a crystalline material, but it can be done, it has been done, and there's people who spend their own lives understanding, determining the structure of glass. This is not our field here. We use information that people gather and publish to correlate with some properties, with crystallization phenomena that we are more interested in. But it's very important then to understand the structure of glasses. So let's take the 5 most common oxide glass formers. For silica glass is tetrahedral, as I have shown here. This is the structure of silica glass. Silicon, oxygen, 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 oxygen. The distance here is about 1.5 angstrom. This distance here is about 2.5 angstrom. This is the structure of silica glass. Well, this structure. This is the unity, the unity that assembles the structure of silica glass. You know, the fundamental unity. How about P2O5? Another famous, glass form is P2O5, but phosphor has a valence of 5. So for P2O5, we have an interesting feature that, you know, there's this tetrahedral, phosphorus is here, oxygen, 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 oxygen. But phosphorus has a valence of 5, so there is a double bond here. This is a double bond, whereas the others are single bond. So by double bond means this is already what is known as a non-bridging oxygen, because it cannot bridge to anything else. The other oxygen can still share with other tetrahedra or with some, for instance, sodium or lithium or potassium. You know, these other oxygens can share, but this one cannot share because oxygen -2 is already completely stable in this position here. So this is for P2O5. So P2O5 has this extra feature. GeO2 is like silica. This has this extra feature. TiO2 is like silica and germanium. And B2O3 does not form tetrahedra. Normally, the pure B2O3 forms, I'm talking about the pure materials. Things change when we add other atoms, but B2O3 forms triangles. Boron, oxygen, oxygen, oxygen. Whereas the others form tetrahedra. However, we can make these pure glasses. Like pure silica glass is a fantastic glass, but it's really difficult to make. You have to melt that glass at 1850 degrees Celsius. It's very, very viscous, very difficult to get bubbles out, very expensive. It's a good glass. There are many uses, but you cannot make common windows of this glass. It'd be too expensive. GeO2 is already very expensive. The chemical is very expensive. P2O5 is easy to make, but the chemical durability is very low. B2O3 is very easy to make, but the chemical durability is very low. So, in glass technology, in very rare occasions, we use pure oxides. We normally add certain elements, such as, for instance, lithium, sodium oxide, or potassium oxide, to help us to make the glass, to melt at lower temperature, for instance. We add to silica glass, drop down the temperature from 1850 down to 1300 or so. But however, they also decrease the chemical durability of the glass. So we add, for instance, alumina or zirconia to increase the chemical durability. What I'm trying to say is that in real life, we add certain elements, and not by chance. People already know more or less the effect of each element to a certain glass. We can, for instance, design a certain glass composition for very high thermal expansion coefficient, for very low, for very high chemical durability, for very low chemical durability, for high density, for low density, you name it, by adding these kind of elements. But in adding these elements, the structures will change. So that's what we are going to see next. How the structures change when we add certain elements which are necessary to produce commercially important glasses. Very well-known glasses, borosilicate. Trade name Pyrex, but there are other trade names. Borosilicate is very much used in laboratory, for instance, because it has very low thermal expansion coefficient, so it does not suffer much from thermal shock. It has a very high chemical durability and low density and other interesting properties that make borosilicate glass an important glass. But here we have already borosilicates, two glass forming oxides, B2O3 and P2O5 and SiO2. And also sodium and other oxides that are added in alumina to improve other properties. So how is the structure of these glasses? And before I move, since some of you do not have a background in glass science, let me just open a parenthesis here and tell you something about oxide glasses. You know, in general, oxide glasses are divided in three categories. We have the glass formers, glass forming oxides. I have already shown 5 of them: silica, germania, boric oxide, P2O5, TeO2, and a few others, As2O3, arsenic oxide, As2O3, antimony oxide, S2O5, and very few others, plus 5 that I have already shown. We also have the modifiers that are added to get the melting temperatures down and to change some properties to break the glass structure. Which are the most common modifiers? Oxides. I know that some of you know, but not everybody knows. That's why I'm asking. Lithium, sodium, all the 1A elements, lithium, sodium, potassium, rubidium, cesium. So the 1A, the oxides of the 1A, of the 2A, magnesium, calcium, strontium, barium, and several others. They're called modifiers. And there are some called intermediate oxides. These are very interesting materials that does not normally form a glass easily unless you use some of the techniques that metallic glass people use. If you quench, like alumina, if you quench it with extremely high quenching rates, 10 to the power 8 or 10 to the power 9 Kelvin per second, then you can have vitreous alumina. But normally, you cannot. If you melt alumina and put it in some table, it will crystallize. But alumina, so it's a bad glass forming material, but can form glass if you add calcium or lithium or magnesium. So they are called intermediate oxides. And there are some intermediate, alumina, niobium, and maybe zirconia, Vitreous, and others. So, glass-forming oxides, glass modifiers, and intermediate. In general, to make commercial glasses, one adds a combination of glass-forming ions, intermediates, and modifiers. And by the way, as a rule of thumb, 50% or so in mole of these guys here to make a decent glass, as a rule of thumb. There are some glasses with a little bit less, but 50 or more molar percent of glass forming oxides. And I think I have already told you, there are 400,000 glass compositions, inorganic glass compositions. Most of these are oxide compositions already invented by man. There are more than that, but there are 400,000 which are included in the SciGlass database. And they have these combinations of these oxides. And this is exactly the project that Graziella is working on now. Well, we are trying to develop glasses with 25 oxides, 35 oxides, glasses that have never been developed yet. This is the idea. But we have to understand, first of all, the simplest systems with 2, 3, 4 oxides, or then perhaps be able to design compositions with 35 oxides without doing trial and error. The idea is not to do trial and error, is to know the effect of each oxide on certain properties and then design the composition based on knowledge, not on purely empirical basis. Anyway, I gave this short review because I know that some of you are not familiar with glasses. Others have seen this in their undergraduate courses. Well, okay, so we have glass forming in modifier cations. If you are working with pure silica glass, pure as silica glass. Pure as silica glass, all the corners of each tetrahedron are shared with other tetrahedrons. When you add one atom of a modifier cation, that bridging oxygen, this is called bridging oxygen, this one here, which is sharing 2 tetrahedrons, is a bridging oxygen. If I add sodium, I form a non-bridging oxygen. This is a non-bridging oxygen because, okay, it's still linked to sodium, but it's not bridging one tetrahedron with another tetrahedron. And this linkage here is is weaker than this one here. So this type of oxygen is called breathing oxygen. This type of oxygen is breathing oxygen, but this one here is a non-breathing oxygen, which is linked to a modifier cation, which can be lithium, sodium, or rubidium, or potassium, or anything. So each atom which is added, it's like a scissor cuts these bridges and form non-bridging oxygens. And this is a nice picture here. In this picture here, sodium, we have silicon, oxygen, and the fourth oxygen is hidden below that plane or here above that plane. So they're tetrahedral, but in this planar drawing, they seem to be triangles, but there is a fourth oxygen which is hidden. But the key point of this drawing is to show that here, the sodium atoms, they're close to this one here, to a non-bridging oxygen. Sodium close to a non-bridging oxygen. Sodium close to a non-bridging oxygen. Close to a non-bridging oxygen. This kind of links here. Non-bridging oxygen. Now with calcium, the valence of calcium is 2. So each calcium has to be close to two non-bridging oxygens. Calcium close to 2. Or strontium or barium will be close to 2 non-bridging oxygens. Sodium, lithium, potassium. Rubidium, cesium close to linked to one non-bridging oxygen. So you're getting now more and more, you're becoming more and more familiar with the structure of glasses. The effect of this modifier oxides break bridges and form other types, more ionic type of links. In doing that, the viscosity decreases, the solubility increases, the thermal expansion coefficient increases. You already start to have a feeling on the effect of these materials on the properties of the glass. And the number of Q3 unities change, Q4 unity changes, and so on. Also, I have mentioned this but did not show a picture. This is a picture of the 6-membered rings in quartz, a crystalline phase of silica glass, 6-membered rings, and here the glass with 10, 2, 4, 5-membered rings. The tetrahedra are exactly the same. You take this tetrahedral here, it's exactly the same of any of the tetrahedral here. Just the links between them are different. So glasses have short range order, but lack long range order. Short range order, okay, they lack long range order. Even when we add these alkaline modifiers or alkaline earth modifiers, the tetrahedra remain the same. We are not changing the coordination number or the size or the angles of the individual tetrahedra. We are just changing the way they're linked. This is like a huge molecule of the size of the sample. We are changing this molecule by adding this, adding that, adding this. Every atom that we add, there's some structural change and then some property change related to this addition. Okay, now let's see the role of the intermediate cations. The role of the modifier cations is clear. They transform the bridges into more ionic, non-bridging oxygen cation linkages. But what happens when we add a glass intermediate, such as alumina or aluminium here? Well, it's very interesting because aluminum has a valence of 3. But for some wishes of nature, when we add alumina to silicate glasses, aluminum takes a coordination of 4. The aluminum, 1, 2, 3, 4 oxygens. So it recovers non-bridging oxygen. It has the opposite effect. So it will recover some of non-bridging oxygen because it takes one more oxygen to form strong links. So now we have, look at this glass here, aluminum coordination 4, aluminum coordination 4. So it has recovered 2 non-bridging oxygens that were formed by calcium in this particular glass. So, well, calcium is still there, somewhere in a complex type of linking, but the non-bridging oxygens have disappeared. So this is like a healing effect. It's a healing effect of glass. So the viscosity increases again. And the thermal expansion coefficient decreases, and the chemical durability increases. So that's why people add some alumina or zirconia or titanium to glasses to recover a little bit part of the non-bridging oxygens. But you cannot add a lot. If you add too much, you are not able to melt the glass anyway. They increase also the melting temperature. So it's a little bit. Normally you add 2%, 3%, 1%, 5% maximum aluminum in commercial glasses to recover. So there's a lot of knowledge which is involved in designing glass compositions. The net effect is that this glass is sodium, aluminum, silicate. It's albite. So albite has the composition of Na2O, Al2O3, 6 SiO2. See what happens here? It's 1 mole of sodium oxide, 1 mole of alumina, all non-bridging oxygens that existed in this class. If we had sodium hexasilicate, you have a lot of non-bridging oxygens. If you add alumina, exactly 1 to 1 mole, all the non-bridging oxygens are recovered, and this glass becomes, this is the viscosity of this glass, very strong and almost Arrhenian. See, this viscosity here is almost Arrhenian because it no longer has non-bridging oxygens. It's not perfectly Arrhenian. Why it's not perfectly Arrhenian? Looking at this, it should be perfectly Arrhenian. It has 0 non-bridging oxygens. It's not perfectly Arrhenian because there are impurities. A real glass has a little bit of iron, a little bit of potassium, a little bit of, you name it, something. So it's not perfectly pure. You can make a perfectly pure glass only in the computer. If you do in molecular dynamics, then you can do a perfectly pure glass. In real life, you never have. Even pure silica, the purest silica, have impurities. OH, sodium, iron. So even pure silica does not have a perfectly Arrhenian viscosity curve. It's a little bit curved because of the impurities. So there is a little bit of non-bridging oxygens in real materials. Now I'm talking about bridging, non-bridging oxygens, bridging, non-bridging oxygens, bridging, non-bridging. Let's do an exercise. I'll give you 3 minutes. This researcher, Stavros, came up with a very simple formula. If you take any glass composition and calculate the number of bridging oxygens, the average number of bridging oxygens per tetrahedron, it's always per tetrahedron, plus the number of non-bridging oxygen is equal to Z, where Z is the coordination number of the glass-forming cation. This formula only works if all the glass-forming cations have the same Z. So I can do this formula for Germania and silica, telluria, silica, Germania, but not for silica, for borosilicates, because boro has a coordination number of 3 and silica has a coordination number of 4. But as long as all the glass forming in the glass formula have the same coordination number, we can use these formulas. And R is the number of oxygens divided by the number of glass-forming cations. Number of oxygens with the number of glass-forming cations. Well, this is in Portuguese. In English, there's no accent. Anyway. So, let's do an exercise. Take your glasses. You guys have adopted a glass for your homework. Let's calculate the average number of bridging and non-bridging oxygens in your glass. You cannot do it because you are working as a metallic glass. And then you cannot do it because you have not adopted the glass. But you can take, for the two of you, I'll give you a composition here so you can have some fun and do some calculation. Let's take this composition here. Calcium, GO2, to SiO2 for the two of you, so you have something to do. The other guys will work on their own glasses, and this will be part of your report. You report the average number of bridging and non-bridging oxygens in your own glass. Let's see. So, let's see. So Graziella is working with a calcium metasilicate. So in a calcium metasilicate, take an example. The coordination number is 4 because it's a silicate, and the R is CaO SiO2. So it's 3 oxygens divided by 1. This is one glass forming cation in the formula. So here will be 4, here will be 3. If you solve these two equations, you come up with 2 bridging oxygens and 1 non-bridging oxygen. That means, Graziella, that your glass has only 2, on average, only 2 corners shared. So they form chains. This is a glass that could form chains, long chains. If this number 3 or more than 2, they form 3-dimensional networks, but if it's 2 or less, they form chains. This is a chain silicate. See how much information you get only by doing these calculations. Huh? What's the number you got for this, Benjamin?
I haven't got there yet.
Você fez, Julian? No, I have not done yet. But to do this, you have to take the coordination. Z is 4 because both silicon and germanium, or silica and germania have coordination of 4. So Z is 4. The number of oxygens is 1, 3, 7. 2 times 2, 4, 6, 7. 7 divided by 2, 3. 7 divided by 3 is R. And then you solve the equation. Okay, guys? Manuel, is that clear? No. What's your glass? What's the composition of your glass? Barium disilicate. So barium disilicate, BaO2SiO2. So Z is 4, and R is 2 times 2, 4, plus 1, 5, divided by 2, 2.5. So R is 2.5, Z is 4, then you can solve the equation. Okay? And see, and I know the result for your glass because it's a disilicate, so it will be Q3, it will be 3 bridging oxygens and 1 non-bridging oxygen per tetrahedron. On average. On average. Okay? Right. So this is a way to calculate the average. The problem is that there is a distribution, but the average can be calculated by knowing the chemical formula of your glass, for any glass. As long as the glass forming cations have the same Z, cannot mix cations with different Z's, because then this formula does not work. So this is the idea of the QN. The N, this N here, is the average number of bridging oxygens per tetrahedron. And this is one measure that you can take this measure from NMR or from Raman spectroscopy. Raman spectroscopy and NMR can give you a measure of N. So you have a glass with 200 components there, you can go there and measure. In principle, it's not so easy to do for a very complex glass, but in principle you can measure N, which is the number of links, the number of bridges per tetrahedron, or per polyhedron, I should say, because some glasses are not tetrahedron, are triangles, other glasses are other types of polyhedron. So it's the number, the average number of bridges per polyhedron. So there are Q zeros. Q zeros are, this is a tetrahedron here in this chart, is not sharing corners with any other tetrahedron. Q1, Q3, this is your, Q2 is your glass. Your glass, you see, it can form chains because it shares 2 corners. Q3s form 3-dimensional networks, and Q4 would be a pure silica, pure germanium oxide, or this albite glass would be Q4. 0 non-bridging oxygen.
For example, if you have 2.5, it's like some of forms chains and some of them forms like tree.
Yes. Because even in your glass is not pure Q2. Your glass, you know, if you had a distribution, this is the idea. You have a probability of being, this is Q0, 1, 2, 3, and 4. Okay? You have a distribution of these guys. Your crystal, this is probability 1. Your wollastonite crystal will be like this. Your crystal will be a Q2 crystal. But your glass, if you do an NMR, this formula only gives the average. So the average will be here, but if you do an NMR, you probably have something like this. Some 30% Q3, some 20% Q1, some 10% Q0, some even some 10% Q4. There is a distribution, and the structure is not clean as in the structure of a crystal. And the more, this is very interesting because the more the glass distribution approaches the crystal distribution, the more similar the structures are. This is one way to see the similarity of that particular feature between the structure of the glass and its isochemical crystal phase. There are many other features of the glass structure. This Q distribution is only one of them. This is like the intermediate range order or medium range order of the glass structure, but you need other information to be able to really construct the structure of a glass, not only the QN distribution. Okay, let me go, oops. So this is the type of plot I was telling you. This is a QN distribution in sodium silicate melts with different fractions of sodium. So this is pure silica. Oh, pure silica is here. 0 sodium oxide is pure silica. So pure silica is 100% Q4. Okay? Now, let's take a sodium disilicate, 33% of sodium. There's a lot of Q3. By the way, this is model calculations. These are experimental data from NMR. You agree very well. So the sodium silicate glass has about 85% Q3, but also has, also has some Q4 and some Q2 and even some, Q1 perhaps. And so on. This is a metasilicate, sodium metasilicate, similar to your volasconite. The sodium metasilicate has about 80% of Q2, but also has, Q3s and Q4s. It's exactly what I told you here. This is distribution of Qs. And this distribution will change with the cooling rate. If you recall the first slide that I showed you, glasses with different TFs also have different distribution of Qs. Not widely different, but enough to be detected. Difference of Q2. So this is the kind of picture that you get using advanced techniques to probe the structure of glasses. And of course, the properties depend on these distributions. But this is a quantitative way to look at the structure of glass. And the same thing for boron. I'm going to finish with this transparency to tell you that boron, of the 5 more famous glass-forming oxides, silica, germanium, P2O5, TiO2, and B2O3. B2O3 has an anomaly, which is very important. That's why I'm going to tell you. With the other oxides, with the 4 oxides, we add a modifier cation. Bridges are broken, and these more ionic, less strong links are made, and the properties in general are deteriorated, like they're less chemically durable, higher thermal exhaustion potential, weaker, and so on. With boron oxide is the opposite. And there's classical paper showing the fraction of sodium. It's difficult to read, but I tell you, sodium, potassium, lithium, rubidium, and cesium. When you add, say, 10% of one of these guys in mole, you increase the fraction of boron in coordination 4. Boron normally has coordination 3, 1, 2, 3. Pure boric oxide is coordination 3. But when we add those elements, we increase the fraction of coordination 4, 10, 20, 30, 40, up to 50% or so of all the boron atoms change from 3 to 4, and the properties improve. This is the boron anomaly. Only with boron, that kind of structural change happens. And this is the secret of one of these very strong glasses used in cell phones. It's one type of glass called glass with native damage resistance. Native damage resistance. When a scratch comes, the boron, these glasses have some boron oxide, changes from coordination 3 to 4. Under stress, this also happens, and consumes part of the energy. So this kind of knowledge, which was published many years ago, 50 years ago or so, this was found 40 years ago, is now being used to make stronger glasses. It's the boron anomaly. The other oxides, if you add a modifier cation, the properties will be degraded. For boron oxide, it will improve up to 30% or so. This is 10, 20, 30, 33% or so. And then they start to decrease again. Boron anomaly. Well, this I have already shown to you, the effect of TF on the structure of borate glasses. Because I'm talking now about borate glasses, but I have already shown this slide. So for today, I'm going to stop here unless you have any questions. No questions, so thank you and see you next week. We'll continue a little bit about glass structure next week, and we will also talk about liquid-liquid phase separation glasses. Thank you. Bye-bye.